Okay, so I'm going to very closely related to induction is inductance. So I'm going to discuss inductance. So for the moment, I'm going to assume steady state. And if it's not steady, I'm just going to use still steady state equations. Yeah. You know, because if you have any change in time and you produce some electromagnetic fields, they propagate out at the speed of light. So they're quickly dissipating. Or if you change the field over a time scale where the dissipation is quick in a way, it is what it is, right? Yeah. Okay. So I just want to recall a few expressions. In this case, the magnetic field is given because of Biot-Savart's law, mu0 over 4 pi. What is the quantity? J, but I'm going to do the loop version. Yeah, you are right. And the vector potential is given by, please check. I dl over r. Because in the quasi-static or in the steady state, it's sort of like a Coulomb's law. Divergence of A is 0, so to speak. And let me confirm that this is in fact the case. Yep, so I have a loop. You have, so typically if it's a current, you're going through the entire loop. Huh? So now suppose I have 2 loops, and I'll just make them look different. Okay, loop 1 and loop 2. So there's dl with a subscript 1, and there could also be a current I1, and I'm not worried about orientation at all. I2, this will be dl2. Okay, so I'm going to look at the magnetic flux on loop 2. So let me explain what this is. Magnetic on N, I'll circle it. On 2 due to 1. Well, that is given by, on loop 2, I do, and look at, mostly this is just notation. It's just keeping tracks of this 1 and 2 business. Okay, so I need the flux, I don't need to circle this guy, I'll only circle it here. So it's the magnetic flux on this loop due to the magnetic field created by this. So it's B dot dA, so it's on this area, so I do dA2, but the magnetic field is actually created by 1. So you see that looking at 1, this I comes out, correct? So this flux will be proportional to the current. Yeah? So what I'll do, Chip, this is B produced by first loop. So this answer is directly proportional to I1. So what I'll do is I will pull out that I1, and whatever the rest of the expression at the moment, it's not very important, I will call it M21. M stands for, of course, mutual induction. Oh, mutual inductance. Yeah. So it's the mutual inductance on 2 produced by 1. Fine. So, and you can write a similar expression. So let me write it here. So you're kind of wondering why it's called mutual. Mutual seems like there's an agreement between the two loops. Worked out a contract, sort of agreed how things work. Well, let's see. So what I'll do now is write B1, so I'm integrating 2. So B1 is nothing but curl of A1, correct? Dot dA2. Well, Stokes' law comes in handy, and I would do on loop 2 A1 dot DL2. Yeah? All right. And so I come back to this one. And, oh, I should have been smart enough to put mu0 over 4 pi. Hold on. At the moment, I'm just putting this. But A1 is this guy. So that's hence. Yeah. So then I have I1, and then it's another integral. Well, A produced by loop 1, and I have DL1 dot DL2 yeah? Agreed? So we see that M21 is equal to, well, I just knock off the I1 and then you can see why this relationship is mutual. I can write this as DL dot right? This is an amazing result. It says the magnetic flux through this loop due to the magnetic field produced by this loop is the same as modulo the current factor, divide out the current, the magnetic flux produced by this on that. When this knows nothing of that and vice versa. So It's a very profound result. And this is what makes this inductance mutual. I'll do a couple of worked out examples, and then I'll do some problems from the back, because the worked out examples are very illustrative. Isn't that kind of neat? Yeah, the math is simple. You write it in your notes. You don't have to remember the math. You can always come back to it. But what's important is remembering that the inductance is mutual. And also, the definition of mutual inductance. This is equal to that. These are the facts you remember. The math, as you know, is trivial. It doesn't seem that. So, let's see. Let's do an example. And what I think this is a standard problem. It's not particularly Griffiths, but it's very illustrative. It is example 710. So he puts a long solenoid in a small solenoid. So example 710. I might change the labelings. He doesn't label them. So let me, so here's a infinitely long solenoid. Maybe since it's infinitely long, I should do it this way. So when I say infinitely long, the advantage here is it's a perfect solenoid. Okay, I'll call this 1. And these are solenoids, so it has some windings, right? So I'll call this N1, being, this is the number density. Yeah? So N1 is winding, number of windings per unit length. Number of windings per unit length of the big solenoid. How many windings are there? Well, infinitely many, because it's an infinitely long solenoid. But the point is, we can assume, we know, if you are this, it may not, obviously it's not infinitely many, but if you're this region away from the edges, we can assume that the magnetic field is uniform. So then he puts an imperfect small solenoid, calls it 2. And it has, I'm going to write it as uppercase N2 because this is not winding density, but just total number of windings. It's finitely 10,000, 1,000, 15,000, whatever it is, right? It's finite. And it has a length, I could call it L2, but there's no L1, so I'm just going to call it length L. Yeah? And what it wants is find phi1, the magnetic flux on the long solenoid due to a possible current in the small solenoid. So there is a current flowing through this, and the current here is I2. Yeah? There is no current flowing through the big solenoid. So a small current flows through, the small solenoid. It's going to create a magnetic field. That magnetic field is going to create a magnetic flux through the big solenoid. And, well, we'll do what we know how to do. This is 1, 2. I2, correct? Magnetic flux on 1 is the mutual inductance times I2. Yeah, the order does matter.
For the M1, 2, or Q1, right?
No, yeah, but let's write it this way first. This is how I defined it, right? So if you look at the previous, description, I better have written please look at this ordering. It should be that.
1, 2, yeah.
Yeah. So here I've swapped. Yeah. But the point is, I don't know how to compute the magnetic field of a realistic solenoid. Yeah. So what do we do? The old switcheroo. What is the old switcheroo? Watch The Princess Bride.
Yeah, I know exactly what you're talking about.
But, okay, fine. What's the movie? The Princess Bride.
Oh, I've seen it.
Oh, yeah. But I could write phi2 as what? M21 I1. There's no I1. But if there were an I1, I could write this, correct? So then, phi1, which is what I want, is equal to phi1 is what I want. Phi2 is what I'm going to compute. Correct? Did I make?
I'm just waiting for the I1 to
disappear.
Yeah.
Yeah. So let's compute phi2. So I'm just going to pretend as if there's an I1 over here, and I'm going to do this. So phi2 is going to be, well, phi2 2 is so it's a magnetic field created by 1. 1 is a perfect solenoid. What is the magnetic field due to a perfect solenoid? Mu 0, little n1, I1. You can see the I1s will cancel. See? Times the area of this. So I think this is radius A. So it's times pi A squared. And how many windings are there?
Why do we need the total energy winding?
Because the flux through this loop, there are in too many loops.
Okay.
Yeah?
Yeah.
Okay. Well, so then, I mean, we're essentially done. Therefore, phi1 is equal to the I1 cancels, mu 0 N1 pi a squared N2 times I2. And I2 was the only current there to begin with. We just invented a fictitious current and a placeholder. Now I can write this as maybe mu0 N1 N2 pi a squared times L. N2 times L is the big N2. Times I2. Yeah? Okay. Clear? So make sure you understand, I over-labeled things for clarity. There's only current in the short one. So we couldn't have, really doesn't make sense to compute phi1 to begin with because there's no, phi2 to begin with because there's no I1. But I just use that as a placeholder. And the fact that these inductance are mutual, so they're equal. And then we get the final answer in terms of what we want. Okay, good.
So, okay.
Go ahead.
No, I realized it now. I was wondering what the difference between the big and little and two is.
Yeah.
Big and two is in little and two times L.
Correct.
Yeah.
L or L2, whatever it is you want to call them. The little n is the winding density.
Mm-hmm.
Good.
So this problem could have been made a lot simpler if it was just a single ring in the middle of the solenoid, right? Because it would be, the only difference would be the N2 and the L.
Yeah.
And then it's just knowing that a solenoid is just n number of little rings.
That's it. Again, you're right. With a single ring, B is impossible to, total flux is not so easy to calculate.
Yeah.
With a single, I think it maybe you can integrate with a single ring. There are no, you can just pick the inside region and just compute the magnetic field. Yeah, but there's an integration involved. So in many cases, you will have noticed that while we employ high power math, problems are mostly algebraic very often, or taking solutions to Laplace's equation, putting it on each side and matching boundary conditions. And boundary conditions may require either continuity or the derivatives have to agree or something like that. It's not, so this is the power of theoretical analysis. You reduce the problem and then you're able to solve it. Okay, so there are many features of this. So if you have a circuit here, so it could be resistors and various other things. There could be an EMF induced. And what is the EMF induced? Minus d phi dt. And this is minus d dt of some inductance. Now I don't have to put a label. I'm not saying 1 or 2 or anything like that. Inductance due to everything times the current. Now remember, the shape of things are not changing. Yep, so EMF could be minus m times di dt. So the EMF induced is not really dependent on the current, but rather how fast the current is changing. Now, if you have only one circuit and current is flowing through, let's put some resistor, let's put a battery, yeah? And there's a current flowing through it. But the current creates a magnetic field. That magnetic field is threading this surface. So you don't need a second surface to induce. You can have self-inductance. Instead of calling it M, it's referred to as L. And the only, that's just how do I get the units for this? Well, that's easy. This is what? Volts. This is amperes per second. Yeah? So it is volts divided by amperes per second. It's called a Henry. So let's do another example problem. The self-inductance manifests itself as a back EMF. Yeah? So suppose you have say an iron that you have plugged in, and then when you pull out the plug from the wall, all this EMF is trying to induce an EMF in the opposite direction. When you pull out a wire, you are taking the current from some value to 0. That's pretty fast dI/dt. And what does inductance want to do? It wants to do the opposite, meaning restore the current. So there's an arc. Yeah, that's what back EMF does. Suppose you are plugging in a current. So you won't find its arcs. It's 0 to begin with. Yeah? So there's not, it's trying to restore 0 so it doesn't have to arc. Yeah. So the best thing to do when you're unplugging something is turn the device off and then unplug it. So let's do another problem. We'll do a couple of problems on the back as well. I want to do what is toroidal coil, okay? Self-inductance. So you have a toroid. And it's a rectangular, my precious stack. John, did I say my precious? Oh my God. Well, there's a little hobbit in all of us. And Sauron is up and about. So a toroid, it's a rectangular toroid. Hey, what do you know? It's example 711. What is a toroid? It's any shape, but in this case it's rectangular, but it's a winding that wraps around itself. And remember, the shape doesn't matter. As long as it is symmetrically wrapped, we know exactly what the magnetic field is. But in this problem, it's a rectangular toroid. So you have, so this is the axis of symmetry, and here is a loop, but mind you, it is not a loop, it is a toroid. So remember, at the end of the day, it is sort of a donut we're talking about, yeah? It is. So let me get the dimensions. And it says find the self-inductance, but let me, so this distance is A, and this distance is B, and this distance is H. And it has a total of n turns. Because it's a finite, it's rotated. Now, let me recall it's written right here. Which way is the magnetic field? Well, it's either this way or that way, depending on which way the current is looping. Our answer won't depend on that. So let's do this. Let's assume E is going that way. So B is proportional to phi hat. And there's a current through the toroid, and the magnetic field is given precise. We did this as a problem. The question is, what's the inductance? So what we will do is we'll just compute d phi dt, and well, we're going to so precisely use this expression, right? So let's look at the flux, magnetic flux. So magnetic flux is going to be what? Well, it is B dot dA. So that is, you can see if I go the right way, dA is also in the phi hat direction. So we don't have to worry about which way is the vector component. So there's going to be an integration here because the magnetic field depends on where we are. Yeah? So this side will have the maximum magnetic field and it decreases. So there will be an integration. But I can pull few of the things out. It is mu 0 n I over 2 pi. And then I have B dot dA. I have 1 over S ds. It's going from A to B. But this is dA. I need 2 dimensions. But in this dimension, it is constant. So I can just multiply it by H. This is easy enough an integral to do. Okay? And this is equal to mu 0 and, did I forget something? I did. Because how many windings are there? N windings. So there's another factor of n. I have one from here. Then there are n windings. Yeah? Mu 0 n squared I over 2 pi natural log of B over A. That's the magnetic flux. And in magnitude, it is L times I. Huh?
The 2 n terms, I'm not sure.
Yeah, let me, it's poorly written. This is the magnetic field. dA is ds times H. Are you good with that?
Mm-hmm.
This is the flux through one loop. How many loops are there?
I don't know, I
Yeah.
guess. If we already have the n
gives you the magnetic field for a toroid.
Okay.
Yeah. Times n. So L is just phi over I, and I think I wrote the answer, mu 0 n squared over 2 pi h natural log of b over a. As I write this, I feel like I may have dropped a term or two. Nope, that works. This is the self-inductance. The very next example in the book, it's a worked out example. It's a standard one. You've seen it in physics too. Please go through it. It's fairly easy to read, but I want to do one problem in the back. Chip, you're okay with it? Yeah, so it appears twice, one in the expression for B and one for the number of turns. Self-inductance is not easy to calculate all the time, but back EMF is and current is. So you can then divide it out and see if it is in fact a constant, and that's what the self-inductance is. So let me do a problem from the back. I want to do problem 726 because I thought it was a toroidal coil. So, yeah, and it is. So, which is handy because I have that expression, but maybe we don't need that when I look at this problem more carefully. So let me hang on to that for the moment. It says, this is problem 726. So you have an AC current. Hey, we're quasi-static, remember. And I is some I0 cosine omega t. They have inner radius, flows down toroidal coil, so it is a donut, if you will. Inner radius 1 centimeter, so axis of the toroidal coil with a rectangular cross section. And to integrate this might be a problem if it was a round one. And this is, you don't mind if I just do it as A, B, and H. They've given values for omega and all of that. Let's not put numbers in. I wouldn't even know what to do with numbers anymore. So for example, they've given frequency to be 60 hertz. So the point is, you have to remember things like omega equals 2 pi f. So if you have AC that is 60 hertz, omega is 2 pi times that. And the question is, in the quasi-static approximation, what is the EMF induced in the toroid? So the magnetic field here too is in the phi hat direction, but it is Ampere's law. It is mu 0 I over 2 pi s phi hat. And what did they want? I forgot. What is the current in the resistor? So is there a resistor? Yeah, the coil is connected to a 500 ohm resistor. So you can even imagine the coil having a resistance of 500 ohms. That's what's going on. Okay, what's the induced EMF? So part A. So easy enough. Minus d phi dt minus d dt B and I. I'm going to put the I here because it's I does not depend on position. It's just the current in the wire, but I have to take the derivative of I over here. So mu 0 I over 2 pi, again ds over s times h. That is the magnetic flux through one loop. And there are how many loops? Do they mention? It's some n, right? Yeah, 1,000 turns. N. So that is equal to minus. We're experts now. What's the derivative of this? Minus I0 omega sine omega t. We've taken the time derivative now. And then we have a mu 0 over 2 pi h times n natural log of b over a. That's the EMF. Well, what's the current in the resistor? Ohm's law. They've given it as 500 ohms. You take this and divide it by R. Lack of space, I'm not writing more. I think there's a part B. Calculate the back EMF in the coil due to this current. So I'm glad I didn't erase. Now this current creates a self-inductance. So back EMF and this is quasi-static, of course. You have to take this derivative one more time. And we need to keep that expression. Oh my God, so let me do it this way. Minus L mu 0 n squared over 2 pi h natural log of b over a. The derivative becomes what? I0 omega squared cosine omega t mu 0 over 2 pi h n b. So and also they want something. What is the ratio of the amplitude of back EMF and the direct EMF? So I'm going to put this as back EMF, and this is the direct EMF. Did I make any mistakes? So, final part, in part C, there's a point here, back EMF over direct EMF. I don't worry about the magnitudes, okay? So it is mu 0 n squared over 2 pi h natural log of, I'm not simplifying anymore because I have to cancel I0 omega squared cosine omega t mu 0 over 2 pi h n natural log of b over a divided by sine omega t mu 0 over 2 pi h n natural log b over a. So I can do this and this, I can do this, this, I can do this, this. I can do this and this. The rest of the details shouldn't matter. I mean, sine and cosine. But look at this, it goes as n squared. Mu 0, n squared over 2 pi h, omega cotangent omega. Yeah? There's an incredible back end.
Is this supposed to be negative?
Magnitude. Just,
Oh, okay.
Yeah.
Yeah, that's good.
I just, just ratio voltages.
Yeah.
But you're right. Cotangent has issues, right? So something non-static has to happen, non-quasi-static has to happen, so that things are finite. The universe won't blow up if you put a current right in the middle of a toroid. So, I mean, cosine can go, cotangent can go to infinity. So obviously our quasi-static approximation breaks down. There are other complicated features. The book, of course, wants you to put numbers in. But any questions?